when considering the rotation and deformation or deflection of a beam, this should look familiar to you. We've talked about this previously when discussing the strain distribution and stress distribution in a beam in bending. So we're going to assume that it curves into a circular shape under uniform moment. So what this is going to give us is if we look at this cross section right there, we'll have a strain distribution like this, where we have compression above the neutral axis because this portion is getting shorter, and we'll have tension below the neutral axis. And we're going to have the strain at any given point as we move up or down away from the neutral axis. The strain is going to be equal to negative y, that's the distance from the neutral axis, times the moment, which is probably a function of x. Let's just keep that as a function of x, divided by the second moment of inertia and the Young's modulus, which we can pretty safely assume are not going to be functions of x most of the time. So with this equation, what we can do is we can plug in the radius of our rotation, rho, in for y, which is going to give us 0 right there for the length, which means we've got to have a strain of -1, which is of course ludicrous as far as a physical object goes, but we're just continuing this all the way up to the center right there. So if we pop rho in there, this must be -1, so we're going to end up with, and I'll pop that negative sign over there so we get plus +1 is equal to rho times the moment, we'll call that a function of x, divided by second moment of inertia and the Young's modulus. So, good news, the curvature, which we can define by the radius of the curvature, is only really a function of the moment and the cross-sectional values of the second moment of inertia and the Young's modulus, but we don't need to worry about any other variables involved, and these will probably be constants most of the time. So now we get to a trickier thing. That's going to be, if we're looking at, oh, that was supposed to be a straight line. Pretend with me. We've got something like this, a curvature, a deviation from the straightness. We've got our value of y right there, and we've got this ray that is tangent to it at this point. Then our rotation at this point, make that a straight line, is going to be that same rotation there. It's a function of x. It's going to change as we move along this length. So we're going to be able to write that 1 over rho is going to be equal to the second derivative of y, our deflection, divided by 1 plus the derivative of the deflection squared to the 1.5 power. And that looks very ugly, and presumably some of you are pretty terrified of having to deal with that. But remember that this value, the slope, is actually going to be quite small in all of these cases for any realistic beam. So this is going to be quite close to 0. And then we're squaring it, and then we're adding 1 and taking that to the 1.5 power. So all of this is approximately equal to 1. So we can go ahead and say that this is approximately equal to the second derivative of the deformation. But I'll have to change page. Let's just slide that on up. Not that far. But we've already got a value or an equation for 1 over rho, right? Or rather, we have this equation we've already determined. So we can rearrange that and say that 1 over rho is equal to the moment at that point divided by our second moment of inertia and our Young's modulus, and it's also just about equal to second derivative of the deformation. And now I'm going to completely switch papers, and we can also write, based on this, that the rotation, which is going to be a function of x, is going to be equal to the derivative of the deflection. So, and that's going to hold for small rotations. So, for this, we have that the rotation is going to be the first derivative of the deflection, and the moment divided by, let's draw that again, right? The moment divided by our second moment of inertia and our Young's modulus is equal to the second derivative of the deflection. Now, if we integrate all of this, we've got that we can integrate this to find that we've also got that the shear is equal to the derivative of the moment with respect to x, and also that the distributed load is the derivative of the shear with respect to x. So, what we can do for all of these is we can basically just keep integrating our distributed load. We integrate it once, we're going to get shear. We integrate it twice, we're going to get moment. We integrate it 3 times and divide by the second moment of inertia and the Young's modulus. We're going to end up with the rotation as a function of x. And if we integrate it one more time, we're going to end up with the deflection itself. The shear is the derivative of the moment, and the distributed load is the derivative of the shear. So we can just integrate the distributed load to obtain our shear function, integrate our shear function to obtain our moment function, integrate our moment function, and divide by the second moment of inertia and the Young's modulus to obtain the rotation, and then integrate the rotation to obtain our deflection.